Welcome to the office. We want to take a look at homomorphisms today. Now, we've already heard of the word homomorphism through our discussion on isomorphisms. So an isomorphism is a one-to-one and onto mapping that maps one group to another group. Two groups are isomorphic if they have the same sort of structure, right? So the homomorphism property says that if I combine two elements over here, let's say addition in both cases, but if I add two elements over here and then map it over, that's the same thing as mapping over those two elements and then adding them, right? So there's the preservation of this binary operation. So the two structures have the same binary structure, right? The two groups do. So that's what we've taken a look at before. But again, isomorphism, where that mapping is one-to-one and onto, right? It's bijective. In the case of just a homomorphism, we're not concerned about the one-to-one or onto nature of the mapping. We're only concerned with whether or not it preserves the operation. So let's assume that we're preserving the operation. Then let me just try to remind you as to what we're looking at between an isomorphism and our different scenarios for a homomorphism. So if I want an isomorphism, I might take my group G and map it to G prime. So phi is a mapping from G to G prime. And what I would need is however many elements there are over here, I have the same number of elements over here because it's one-to-one and onto. So this is going to get mapped to there, this maps here, this maps here, and this maps here. And because the binary operation is preserved, essentially they're the same group, right? That's what we're trying to emphasize here. We even go so far as to point out that the identity element over here gets mapped to the identity element over here. And if we have some subgroup over here, then when we map that subgroup over to here, it's also going to be a subgroup. Or if we have a subgroup over here, then what's over here that maps to it must be a subgroup, right? We have all of these nice results for isomorphisms. And the reality is that most of those are going to hold for the general homomorphism because those properties, right? The image of a group is a group. That didn't depend on the fact that it was one-to-one and onto, not at all. It only mattered that it was a homomorphism. Same thing for the pre-image of a group or the pre-image of a subgroup. So we have the image of a group, the image of a subgroup is a subgroup, and the pre-image of a subgroup is a subgroup for isomorphisms. But again, the only thing that mattered was that it was a homomorphism, not that it was one-to-one or onto. So essentially, we're going to end up with a few different possibilities here. For a homomorphism, of course, an isomorphism is a homomorphism. It's a special case where it is one-to-one and onto. For a homomorphism, you could have fewer elements here than you have over here. And so you could map something like this. Something like this. Let's see here. I think I put too many elements over there. We'll look at the relationship between the number of elements shortly here. Let's see here. Oh, no, I had the right number of elements. Okay, sorry. Anyway, so I mapped this over. Again, identity is still going to map to identity. That was a result of homomorphism property, not a result of bijective property. So we still get those sorts of things, and we'll still have that the image of a group is a group, and we'll still have that the pre-image of a group is a group, right? We're going to have all of these same sorts of results. It's really quite nice. But the main thing is that we don't have to actually map to everything. So we could have this scenario. We don't have a map to everything. And we could also have this scenario where we have more over here. Oh, so I didn't maybe complete my labeling. I apologize. Let's go homomorphism here too. Of course, these can't be isomorphisms because they're not one-to-one and onto. So I'm going to map G to G prime again. But it might be the case that there were more things over here than there were here. So I want to map to there. and map to there, and map to there. It's not going to be the most interesting example, and that's okay. But then I'm going to start sending things to two things to the same place. Okay, I'm going to cover it up twice, and that's fine. One of the things that's also going to be interesting to us, or that we might wish to know, is what are all of the things that map to the identity in G prime? That's actually called the kernel of the homomorphism. The kernel of the homomorphism is all of the things that map to the identity. So here, this element maps to the identity as well as this element. So these would be the kernel of the homomorphism. And the other examples that we drew, there was only one element in those kernels, and that's fine. But we could have more than one element. But this over here actually works out to be a group, and the kernel, that group, is of special interest to us. So this is sort of a nice preview of all the sorts of things that we're going to talk about throughout this section. But the main thing, again, is a homomorphism is essentially just like an isomorphism, except we don't care about one-to-one and onto. So it's just a mapping that preserves the operation. All right, we'll take a look at a lot of examples for this section, try and get a good comfort level with the idea of a homomorphism, because then we're going to go ahead and continue that idea, especially focusing on that kernel as we move into later sections. So thank you for your time. Let's continue taking a look at section 12 here on homomorphisms, 13 rather, on homomorphisms.